Today we're going to talk about momentum. And momentum means that if you have a certain amount of mass and it's moving forward in a certain direction, all right, then when it hits other things, you still need to have the equivalent amount of momentum when you're done. When something hits something else, the momentum before has to equal the momentum after. And it has to do with two things: how fast something's going and how much mass it is. The more massive and the faster things go, more momentum you have. So two of these little balls have more momentum than just one. So if I pull back two get knocked out. If I pull back three get knocked out. You can even do really crazy things, like pull back 2, 4, 6, and 6 get knocked out. All right? So that's momentum. However much you start with is how much you end up with. So if I take a really big ball like this and knock it in, it knocks a bunch of them out. Okay? So that's basic momentum. This week we're going to talk about angular momentum, which is a little bit different, but it's kind of cool. And it has to do with momentum as it goes around in a circle. But the basic idea is still the same. If you start with a certain amount of angular momentum, you're going to have to end with the same amount of angular momentum. It's not going to go away. So this cool toy is going to demonstrate angular momentum. We have two big balls here, and they can slide in or be slide out. All right? And I can pull down when I pull on this. And so if I get this spinning, there's a certain amount of angular momentum associated with the weight of those balls, and it depends on how far they are from the middle, basically how fast they're going in their circle, right? And then how much mass they have, and they have a lot of mass. So if I take this little handle down here, I can pull down and slide the balls in, and they go a lot faster. Or I can let it spread back out again. So once again, if it's spinning along, and then we move the mass in, we have to have the same amount of momentum, so it's going to speed up. Why is that? That's because when they're far out here, they're moving along at a good clip, they have to keep that same momentum, angular momentum, when they're in closer, and to do that it has to spin faster. We can apply our new knowledge of angular momentum to explain how ice skaters and dancers can spin really fast and also sort of not fall over, but helps them spin very fast. So I have weights on the ends of my arms here. I'm holding on to these, and if I put them out, I'm going to have a lot of angular momentum even if I'm moving slowly. All right? And then if I pull the weights in, I will have to speed up to keep the same amount of angular momentum. And then I'm dizzy. Time for some practical applications of angular momentum. I've got here a bicycle wheel. All right? And angular momentum helps you ride on a bicycle. If I spin this wheel up and get it going really fast, I now have angular momentum in this bicycle wheel because it's spinning around the entire wheel has angular momentum. And it so happens that if I try and turn the wheel a new way, it will fight against me. It won't let me turn it just a little bit. And it turns out that because it has all this momentum, it actually helps you stay upright when you turn your bicycle. And it keeps you from falling down once you get moving. And I can also use this to turn. So now I can use that angular momentum of the bicycle wheel to spin myself around when I'm on top of a little platform. If I turn the bicycle wheel, I start spinning. And then if I turn it straight, I stop. And I can spin back the other way, one way, and then spin back the other way. Well, anyway, I can spin one way really fast. This is Dr. Carlson, orbiting myself, and I'll see you next time.